We've already looked at electrochemical cells and calculating EMF, but one thing students often get confused about is how salt bridges actually work. Many students incorrectly believe that electrons flow through the salt bridge, and this gets picked up on by examiners year after year. So in this video, I'm going to break down exactly what salt bridges are, how they work, and what they should be made from so that you don't lose easy marks in your exam. So just what are salt bridges? Well, salt bridges are usually a U-shaped glass tube filled with a soluble ionic compound. Or sometimes they could be a piece of filter paper soaked in a soluble ionic solution. And they physically connect the two half cells, forming a bridge between the two electrodes. But why do we even need them? What's the point? Well, the key idea is this. The salt bridge completes the circuit by allowing ions to move through it. In electrochemical cells, electrons flow through the external circuit from the half cell where oxidation occurs to the half cell where reduction takes place. A common mistake is to think those electrons pass through the salt bridge. They don't. The salt bridge only allows ions from the electrolyte inside the salt bridge itself to move. And this movement of ions prevents charge building up in the half cells, allowing the redox reaction and therefore the flow of electrons to continue. So once the salt bridge is in place, we have a complete circuit. The electrons flow through the external circuit and ions flow through the salt bridge. But for an ionic compound to be used within a salt bridge, it must meet two requirements. Firstly, it needs to be soluble in an aqueous solution. And this is so that the ions are actually free to move. A salt bridge made of ions that can't move is utterly pointless and just doesn't work. Secondly, it can't react with the solution in either half cell. If it does, it changes the position of the equilibrium within that half cell and therefore changes the overall EMF of the cell. Now, if you're asked to name a suitable ionic compound to use in an exam question, I would always go with potassium nitrate or sodium nitrate. You aren't expected to know solubility rules, but all nitrates are soluble, and both potassium and sodium nitrate are pretty unreactive, so they're unlikely to react with any of the solutions you'll commonly come across in exam questions. Now, a common exam question linked with this is to explain why a particular substance isn't suitable for use in a salt bridge, and there are only two reasons for this to be the case. It's either because the substance is insoluble in water, or because it will react with one or both of the solutions in the half cells. Since you're not expected to know solubility rules, it will generally come down to the named substance reacting with one of the solutions in the half cell. However, you need to say how. Usually, this requires you to recall content from elsewhere in the spec. Now, there are lots of possible reactions, but the most common ones to look out for are neutralisation or precipitation reactions. Neutralisation reactions will occur if your half cell contains an acidic solution and the proposed salt bridge electrolyte was a metal oxide, hydroxide, or carbonate. So you're looking for combinations of acids and bases. Precipitation reactions are usually linked with your knowledge of testing for ions, and a common example is combinations of halide ions and silver ions. So for this one, you're trying to spot a substance you're supposed to know the chemical test for. Regardless of what type of reaction is occurring, if your salt bridge electrolyte reacts with one or both of the half cell solutions, this will ultimately affect the EMF of the cell, and so it cannot be used. So now you know exactly what salt bridges do, how they complete the circuit, and how to tackle suitability questions in exams. Next up, we're going to be looking at representing electrochemical cells, or if you need more support, you can work through the full playlist.